Hello friends. So, we are into the practically the last lecture of week 5, and we will continue our discussion on primary sedimentation as we were discussing in the earlier week. So, we did talk about the basic theory of sedimentation and what are the different zones of the settling tank. Now, we did discuss that there are a couple of designs of sedimentation tanks. Sedimentation tanks are primarily either rectangular type or circular type. Of course, there are others few other variants of this design is also available. So, like we can have a square sedimentation tank as well, but those are generally not preferred. So, the most common design of the sedimentation basins or settling basins are either rectangular sedimentation basin or circular sedimentation basin. So, if you see a rectangular sedimentation basin, the inflow comes in here and then it first goes to a inlet zone, as you can see from here, and then it passes through settling zone, eventually moves to the outflow zone and sludge is collected over here. So, these are the different zones, the 4 zones that we discussed in the earlier lecture for a rectangular sedimentation basin. We can have a sort of device like this, blade like this, which can be used to rotate in order to push the particles which are being settled downward and eventually bring them down to the sludge zone. In practice, in field, a typical rectangular sedimentation tank will look like this. So, this is your settling basin. Of course, here would be your then inlet arrangement, and then the water from here goes to this through these weirs goes to these launders, and these connects eventually to the outflow zone. So, that becomes your outlet arrangement, and this is where this is basically the settling zone or settling basin. So, this is outlet zone, settling zone, of course, the other zones that way are not visible in this one, but that is how a typical rectangular sedimentation basin or settling tank looks like. Now, if you see the circular sedimentation basin, it is actually in the circular shape as can be seen here. So, the typical flow arrangement in a circular sedimentation basin would be like this. You will have one will have an inlet from bottom. So, circular sedimentation tanks are mostly upflow type. So, you will have inlet from here and then the water is pushed from this point forwards, it goes here. So, this becomes your inlet zone. This is where the initial turbulence is subsidized, okay. And then from here this arrangement, the water comes and then water raises up through these, it crosses these weirs to go to the outlet zone. So, your outlet zone will be these weirs and it is across the periphery. So, as you are seeing in this picture, this whole thing is actually the from this weir, whatever is the overflow, generally overflow goes there. So, overflow from all these things will be connected to this weir, and that becomes the outlet zone. This is what you are seeing primarily is actually the settling zone and the water which is being pushed this point forward. So, here there is your inlet zone, and of course, in the bottom of this tank there would be sludge zone. So, that way the overflow is pushed here, settling process primarily takes place in the settling zone. So, this becomes your settling zone, the large portion of the tank, and the particles settle down, and then we have a mechanism to push those particles back here, and then from here they can be collected. So, the bottom part obviously will become the sludge zone. So, that is how it is, the flow is in the upward direction typically, the inlet is in the center, outlet is across the periphery, and the other major part or central part of the tank, this entire portion of the tank is actually your settling basin. So, the main settling zone. So, that is how a typical circular sedimentation basin is conceptualized. Now, if we see the theory of settling or how particles settle, the model of settling. So, let us say consider we have a particle of dia d which is just removed with a settling velocity of Vs. Just removed means that this particle, as we discussed earlier, that a particle in a settling basin a particle is considered to be removed when it hits the bottom part of the tank, when it hits the anywhere in the sludge zone. If it is hitting here, if it is hitting here, if it is hitting here, we will consider that as a removed, but if it let us say hits here, so we will not consider that as a removed, we will consider that particle as not removed. Okay. So, that way we have, if we consider a particle which is just removed, that means we are talking about a particle which has just hit the this corner and enter into the sludge zone, because any lower settling velocity will lead this particle to hit the outlet zone, and then this particle will be washed out from the tank. So, this is important to see at what velocity the particle is just removing, because this provides us the critical velocity. So, any settling velocity is higher than the velocity of this particle will get settled, settling velocity lower than this particle will not get settled, as per the concept of ideal settling theory. So, if a particle is just removed with a settling velocity Vs, then the sort of if we see the settling basin which is of size L b into h. So, length of the basin is L, height is h, and of course, the third dimension width which is not visible will be b. So, in that case the settling velocity of the particle, what would be the settling velocity of the particle? So, if we see the downward velocity, settling velocity through which it has settled, so it has in t time, if the particle has spent let us say t time in the reactor. So, in t time the particle which has entered here has travelled this much of vertical distance. So, this is the vertical distance it has travelled. So, the vertical velocity will be equal to the distance covered divided by the time taken in covering this distance. Now, when we are considering a particle, for a particle which is just removed, means if a particle entering here with the same settling velocity, it will obviously be easily removed, particle entering here will obviously be easily removed. So, just removal, the critical case is the particle which is entering at the top and still getting removed. Okay. So, that is why we consider this case. So, h is let us say the height where the particle has entered. So, it has travelled h distance in t time. So, its settling velocity is going to be h by t. Now, we know that t is the detention time of the tank, okay, and the detention time will be equal to the volume over flow rate, okay, because if the total volume of the basin is say 500 meter cube and your flow rate is 50 meter cube per hour or say per minute. So, if your flow rate is 50 meter cube per minute for a total volume of 500 meter cube. So, that means your 50 you can assimilate 10 times. So, 10 minute is going to be the detention time. So, V by Q is your detention time. Now, if we replace this with the detention time, so it becomes h by V by Q, and V is your LBH, Q goes up. So, that way we can solve this and we will get Q by LB, or length into width is actually the plan area of the tank. Okay. So, this eventually becomes equal to the plan area of the tank. Now, if you recall Q by A from earlier lecture, we discussed that if we divide the flow with the plan area of the tank, what we get is the surface overflow rate, or what we call as overflow rate also. So, for a critical case, the settling velocity of a particle is going to be equal to the overflow rate, or in other way we can say a particle having settling velocity equal to overflow rate is likely to be removed, and particles with lower settling velocity may not get removed completely, or particles with higher settling velocity, because velocity is high. So, they will easily get removed that way. So, the volume of water which flows in a unit time per unit surface area in the settling basin is typically known as surface overflow rate or overflow rate, which is equal to the flow rate or discharge Q divided by the plan surface area of the tank A. Now, the unit of discharge would typically be meter cube per second or meter cube per hour, and unit of surface area is meter square. So, that way this unit becomes equal to the velocity, but overflow rates are not presented in a unit of velocity. Okay. For the unit of velocity or unit of settling velocity or flow through velocity, we typically represent as meter per second. The unit of overflow rate is also same, but it is not presented in a meter per second, but rather in meter cube per meter square per second. So, that way it will eventually be equal to meter per second, but if you see the point of putting it as a meter cube per meter square per second, because this gives you a better idea that it is the flow rate which is in the meter cube per second divided by the surface area of the tank. So, that is how the overflow rate is conceptualized. Now, other way also, if you see that you are putting a flow through a tank and plan area of the tank is say A, which is your L into B. So, plan area of the tank is L into B and you are putting the flow. Flow is as we were seeing earlier, just when we are looking at the rectangular or circular sedimentation basins. So, you see here that it is actually the overflow from this area which is the overflow from this area which is eventually get collected in the outlet. Okay. So, when we say the surface overflow rate, means from the entire surface how much flow is actually going out, okay, per unit area. So, this is the total discharge. Obviously, what is the inflow, the same amount will be actually coming out in equilibrium, the inflow is going to be equal to the outflow. So, the discharge of the outflow is going to be the same, but what amount is being spilled out per unit area of the tank is what is your surface overflow rate. So, that is why we call it is a overflow from a surface of area L into B, okay, or in this case in a circular case pi d square by 4, which is the area of the tank that way. So, this way we can have an estimation of the surface overflow rate which is going to be equal to settling velocity, and this is actually one of the critical information which is typically used while designing the tank. Now, if a particle with settling speed or settling velocity Vs, its vertical fall, how much it is going to fall will be equal to h by t, because as we defined earlier Vs is equal to h by t. So, h, the vertical fall a particle will take, will be equal to its settling speed into t. So, if a downward settling speed of the particle is let us say Vs and it is spending t time in the tank, so the total distance it is likely to cover h will be equal to q settling velocity times t. So, that is the total vertical fall a particle is expected to take. Okay. Now, if you see, as we were discussing, if we let us say define something which is called critical settling velocity or critical settling speed, okay, which is the velocity for which all particles of a specific diameter gets just collected. So, means they get just removed. So, that is the critical settling velocity. So, if we have a tank of say height is equal to h, the total tank height is h. So, a critical settling velocity means particle of dia any specific dia is just gets collected. So, as we were seeing earlier, so that means this is going to be the trajectory of the particle in consideration, and the settling velocity or vertical velocity of this particle Vc, which is critical velocity, is the one which will guide this, okay, it is which is being indicated as it is getting just collected. So, if it is just collected means anything lower than this will obviously be collected, higher than this may not be collected, and that is why we call it just collected. So, your critical settling velocity in that case is going to be the depth of the tank, which is capital H divided by T, or we can have in a same way which is equal to Q by A or V 0. So, this is equal to the overflow rate. Now, for design purpose what typically we do, we estimate the critical settling velocity or estimate the settling velocity of a particle which we want to settle from a Stokes law or that some measures, and then equate that to the overflow rate, and when we equate that to surface overflow rate. So, we know the Q value and we know the settling velocity of the particle, critical settling velocity of the particle. So, that way we can determine the plan area of the tank. So, if we try to see the efficiency of the particles which are settling. So, because V c is the critical velocity, okay, this V c is the critical velocity. So, any particle which is having the velocity or settling velocity greater than this critical settling velocity. Okay. So, if V s here is say greater than V c, so then H here is going to be actually, because H is equal to V s times T. So, a particle, the vertical fall a particle attains here actually is equal to its settling velocity times T, right. And for a critical settling velocity, the vertical fall that a particle attains is H. So, if your V s is equal to V c, your H is equal to H in that case, but if your V c, if your V s is larger than V c, okay, if your particle is settling at a speed faster than V c, okay, if your if say the selected particle or the desired particle is settling at a faster speed than V c, in that case your the H that you are going to get, which is equal to V s times T, and V s is being greater than V c. So, your H eventually is going to be greater than H, capital H. So, the fall that particle will take or the distance that particle can travel in a given amount of time is actually going to be the greater than the depth of the tank. So, if let us say this is the case, so particle starting from here, if its velocity is higher, so it will actually it can travel, the typical H is this much, but in the same time it can travel actually a distance greater than H. Of course, it need not to travel this distance because it will hit the bottom of the particle, but that means it is going to hit the bottom of particle much before the corner. So, all such particles with higher velocity is bound to hit the bottom of the tank and will not go into the outlet zone, and that way all such particles will get collected in the tank and we will have 100% collection efficiency for all such particle which are having settling velocity greater than critical settling velocity, as their the vertical distance they can travel is higher than the depth of the tank, and that is why they can easily get collected. On the other hand, the particles which are having settling velocity slower than the critical settling velocity. So, in that case if your V s is smaller than V c, so the H you are going to get is actually smaller than capital H. Now, a particle may need to travel this capital H distance in order to get collected if it is entering at this point. So, for such cases the particle which is entering here will be travelling a distance which is actually smaller than H, and those particles which are entering here or entering here may not get removed because they are not able to travel the entire depth, they are not able to cover this entire depth in the amount of time which they are spending within the tank, and that leads that particle will hit the outlet zone and may get collected. The particles which are actually entering at a depth H, because this is the depth that they can cover. So, the particles which are entering at a depth H or lower than H, so those particles only will be able to hit the bottom and get collected. So, in that case your collection efficiency may not be 100% because these particles are not getting collected while these particles may get collected depending. So, collection efficiency will eventually depend where the particle is entering in the tank or at which level the particle is entering into the basin. So, in such cases your collection efficiency is definitely not going to be 100% because some particles may hit the outlet zone, and as a result you will see that collection efficiency is given by the ratio of H over H, or because the time is same and H as we can write V s into T and capital H as V c into T. So, it is going to be the ratio of the settling velocity of the particle versus critical settling velocity, okay. And that is how this will be the collection efficiency of the particle, and that way we can estimate how much particles are going to be collected in the system. Now, what happens that the size of the numerous particle in the sewage in the wastewater are not same. in ideal settling tank we are saying that the particle having a settling velocity let us say which is greater than Vc or lesser than Vc, but what happens in an actual sample, since your particle size distribution varies over a range of dimensions. So, there is a good gradation of the typical particle size which are present in the wastewater or even in the waters. So, in that case the different size of particles will have different settling velocity, and that way we, like if we want to know the total removal efficiency of the tank, total removal efficiency of the particle. So, we have to consider this entire range of particle having different settling velocities. So, how do we do that? Because theoretically it is not possible, there are n different size ranges of the particle, and it is practically not possible for each and every individual diameter you determine the diameter of the pipe and how much of that particle is going to collected, what is going to be the efficient settling or collection efficiency for that particle, okay, which is going to vary based on the dia and dia. So, typically for such purpose a column test is conducted which is called column settling test, and based on that a velocity settling curve may be constructed depending on the data or based on the data that we have. So, typical column settling test is something like this. We have a column where we collect at different depths, we collect samples at different depths and we determine how much samples have been collected and what is retained in the column. So, this sampling is done at a different time, and based on these different times, so some particles which is let us say being collected here or some particle which is collected here in a time. So, the particles which is getting collected here has a settling velocity of, because it has travelled this much distance in the given time. So, if say time t1, so in t1 time this has covered say h1 distance, while the particle which is being collected here has covered h2 distance and particle which has been collected here has covered h3 distance. So, that way the different particles will have travelled different distances in a any amount of time, and we basically draw this. So, ISO percent removal curve we draw, so 80% removal curve, 70% removal curve, 60% removal curve, 40% removal curve, and based on that we can sort of analyze it. So, if we want to know the total efficiency of the tank, so for a given flow rate q, the particles which are having settling velocity greater than equal to critical settling velocity will be completely removed as we were just discussing, while the remaining particles which have settling velocity less than critical settling velocity will be removed in the ratio of Vs versus Vc. So, the total fraction of the particle which is removed will be equal to 1 minus xc plus integration from 0 to xc and settling velocity versus critical settling velocity by dx into dx. So, what this eventually represent, if you see, now if say the xc is the fraction of particle which is having settling velocity lower than critical settling velocity. Now, if xc is such fraction of particle, that means 1 minus xc is the fraction of particles which are having settling velocity greater than critical settling velocity, and as we know that all of these particles, 100% of these particles are going to get removed. So, removal efficiency will straight away have this component 1 minus xc, because these are the particles with settling velocity greater than critical settling velocity and all of them are going to get removed. While for the smaller particle, the xc fraction, it will depend on let us say, because if we plot this data, so we will get maybe a curve like this, say. Now, this is the fraction removed, say your x. So, what happens that up to this x which is your 1 minus xc is completely removed, and this is your zone of x where only particles which are basically you need to determine the area under the curve. And how we determine the area under the curve? We have to integrate it, right. So, we integrate because Vs by Vc is the ratio of the particle which has removed. So, we integrate this Vs by Vc over a small slit dx, and let us say this is my elementary thickness dx in this. So, I integrate this value from a point here to here or from a point here to here, and So, when I integrate from a point here to here, the area of this curve which I will get on this axis is going to be equal to the amount of particles or fraction of particles which will be removed. So, this is the removed fraction of particles which are having settling velocity lower than V c. So, this is for a continuous curve, we can discretize it also. So, for discretization we can sort of take the small values of dx, and on this curve we can take the, if let us say this is the velocity. So, we can take the average of this and multiply it with the dx. Of course, our V c or critical settling velocity is going to be constant, because V c is equal to overflow rate, surface overflow rate. So, for a given tank size, our surface overflow rate or the critical settling velocity is constant. So, this we can take out, and then eventually what we need to determine from this one is that C being a constant. So, this will be converted as integration 0 to x c 1 upon V c or 1 upon V o, whatever we write, and then V s into dx. So, it is basically this area that we need to determine, and as we were suggesting that if you have a curve like this. So, if we take a small dx and integrate it from point 0 to say x c, this is my settling velocity V s curve. So, this curve, the settling velocity curve, so we will get area under this curve, and for discretized manner we can take a different values of x and corresponding average value and multiply that in order to get the area. So, that is how we can actually determine the net removal for a varying particle size. Now, this concept is practically very useful in terms of wastewater, because in the wastewater it is not always discrete settling or ideal discrete settling. So, for real settling basins there is assumptions of ideal discrete particle settling does not hold true often. That is because there is suspended particles in water, and wastewater generally exhibits a natural tendency to agglomerate. Particularly in the wastewater, if we see, so suspended solids are not like truly discrete particle. There are various lightweight particles, there are various small particles, and when they come into the contact they agglomerate, form larger type of this thing, and as a result their flocculation occurs, and this leads to the type 2 or flocculent type settling which we discussed in the earlier lecture. So, settling essentially may not be the discrete type 1 or ideal settling which we are discussing so far, it may be of a flocculent type settling. In a flocculent type settling is better because settling velocity increases and we can get the particle settle in a lesser amount of time. So, that is in fact not a bad thing to have. However, there is no as such model exists which can sort of describe the flocculent type settling of the various particles or various flocks formation mathematically. So, then settling column analysis is usually performed as we were discussing, and same way we can determine the settling characteristic and removal characteristic of the particles. Okay. So, that is what is typically of very high application, particularly when we design settling basin for wastewater treatment. Okay. Now, the basin efficiency again is not always ideal as we considered for ideal settling basin, and this non-ideal performance similar to the grid chamber that we discussed could be because of the turbulence or short circuiting which results from eddy, wind or density currents. So, the same kind of approach is adopted in order to estimate the efficiency. So, if, this formula would be appearing you familiar because we discussed this in a grit removal sense also. So, it is the same thing, and here the value of n is chosen 0 for the best possible performance. Okay. So, if value of n becomes 0, your efficiency becomes equal to 1. It is considered 1 by 8 for very good, 1 by 4 for good, 1 by 2 for poor and 1 for very poor performance. So, based on this we can if we consider say desired removal efficiency, we know the value of n, we know the settling velocity, we know the discharge. So, we can determine the area from here for an real settling basin and not the ideal one. Okay. So, that is how basically we can design or we can get done the sedimentation part. If we see the various factors that affect sedimentation, there is shape, size, density and nature of the particles, viscosity, density and temperature of the water, then what is the surface overflow rate, velocity of flow, inlet and outlet arrangements, what kind of turbulence they are leading to, what is the detention period, what is the effective zone of the effective depth of the settling zone. So, all these things are the one which decides the efficiency or performance of a settling basin. Now, for design purpose there are several things that needs to be done. So, their first step would be to compute the critical settling velocity for the smallest size of particle to be removed. So, if you want to let us say remove a 0.02 mm size particle, so use this dia, put that in a Stokes law and determine the critical settling velocity. Determine the Reynolds number, see if it is less than 1, fine. If it is not less than 1, go to the turbulent equation, use that dia estimated, use that settling velocity estimated, get the Reynolds number, get the drag coefficient and through trial and error reach a critical settling velocity for the particle of the smallest dia. So, that becomes the very first step. Now, this critical settling velocity is equated or is kept equal to the overflow rate incorporating basin efficiency, and then we compute the surface area. So, as we are just seeing the equation for the basin efficiency. So, considering a like performance of a efficiency or the value of 1 by n or n, what we can do is we can reach, we know the settling velocity, we can equate that to overflow rate. For an ideal settling basin, we can just keep settling velocity equal to overflow rate, okay, which is equal to q by a. So, we know the settling velocity. So, from here a becomes q by the settling velocity, but for real settling basins we will go to we will use the formula which we were just seeing, and then from considering a efficiency of settling and n value and this thing we can compute a from that formula as well. So, once we know the a, we can fix the dimension either in terms of length or width or dia. There are certain criterias which are adopted typically in fixing these dimensions, and then we can select an appropriate depth and detention time. We need to check these designs for adequacy of various design criteria, which would be in the terms of overflow rate, depth, detention time, solid loading rate, wear loading, scoring velocity, etc. So, all these things are checked, and then we can put sludge inlet, we can like sludge withdrawal mechanism and inlet and outlet arrangement, we can design the freeboard, required freeboard we can provide. So, those are the other design aspects which need to be followed. If we see the recommended design parameter for wastewater, for primary sedimentation treating wastewater. So, for primary settling only, the overflow rate should be in the range of 25 to 30, while it could be peak could be 50 to 60. Okay, if it has to be followed by the secondary treatment, we can have a higher overflow rate because some part can be get settled in there as well, and for activated sludge return, if it is there, we can have this range. So, that way there are various criteria for wear loading rate, and then side water depth, what should be the range of side water depth in such cases, because that is what eventually controls the depth in the tank. So, that way we can use these design parameters for the design purpose and cross checking. The dimension of the tank are also sort of guided, that we can have a certain ranges for the dimension. For rectangular tanks, the depth should be between 3 to 5, 3.5 is the typical value used, length should be 15 to as high as 90, but it is 25 to 40 meter which are typically used, and similarly 6 to 10 is the typical range for the width. For circulars, diameter can be as high as 60, but again it is 12 to 45 which are the typical values used, and depth again could be 3.5, we can have higher depth in the circular settling tanks because of its upflow nature. So, that way we can go to a depth of around 4.5. The bottom slope is considered 60 to 160 is the range typically, and 80 is the typical value. If we follow the manual, so CPHO says that length to width ratio should be 3 to 5 times 3 to 5 is to 1. So, either 3 is to 1, 4 is to 1, 5 is to 1 or 3.5, that way. The length 30 meter is common, maximum could go to 100 meter, width is 6 to 10 meter. For circular, diameter should not be greater than 60, generally 20 to 40 is recommended as per the manual. Depth, again a normal depth should be 3%, and bottom slope for rectangular it is 1% towards inlet, while in circular it is 8% towards the center. So, these are the typical design parameters which are used. So, that talks about the main part or main design of the settling zone. Of course, there has to be supplemented with various inlet and outlet arrangement. So, these typical inlet arrangements, as we briefed earlier also, we need to put a say buffel with multiple opening or this thing, so which can evenly distribute the water in the basin, or we can have a system like this inlet pipe from where it skids through and then it through like multiple opening it goes into the main settling basin. We can have a system like this where water is collected on the top and then from bottom it goes into the tank. So, the turbulence portion is subsidized here only. Same design is this one, turbulence portion is subsidized here and the overflow from this goes to in this one, and then there is another buffel which sort of smoothens the transaction into the settling zone. So, these are some of the typical inlet arrangements. Similarly, we have various outlet arrangements which could be in the form of V-notch effluent launders, okay, effluent box or effluent pipes. So, this is a kind of V-notch pipe that you can see here. This is one of the most common and most effective way. So, we can have those V-notches. Okay. We can have outlet with rectangular weir in the form of weir plate. So, through weir plate this actually flows through, okay, flows through this and then come to the outlet launder. We can have launders over here again, the like you are having this kind of channel. So, water which is overflowing from here eventually goes collects in these drains and then from these drains it connects to the outlet chamber. This example of how the overflow is collected. So, this kind of inlet and outlet arrangements can be made which can serve the purpose. The last thing we would like to briefly discuss is that there are certain alternates also to the sedimentation tank. So, these days particularly for smaller setups, because with a large setup it becomes difficult, but for smaller setups or industrial or even some cases water treatment systems, not that in the wastewater, but more into the water treatment, even some industrial effluent treatment systems also, the it is actually plate or tube settlers are used, which are often like considered as kind of Lamla clarifier. So, what happens that water flows through these slanted tubes or slanted plates and particles. So, it is like this, the water which is containing particle will move up on in these tubes or plates, and then particle what happens, it hits the surface and then drifts back down to the lower portion and then settles over here. So, the particles will remain accumulated, will settle and will drift down here, whereas your water can easily flow up. So, clarified water passes through the tubes or between the plates depending on whether it is tube settler or plate settler, and then flows out of the basin. It has a certain distinct advantages. The performance is very good first thing, and then it is a compact unit. So, therefore, the total area requirement, because you do not have as such of like those inlet arrangements, outlet arrangements and so many other things. So, generally the area required is lesser than that of the conventional clarifiers. It can be as low as 65 to 80% of the conventional clarifier, or alternatively if you have a size of clarifier and you pack with such systems, you can deal with the larger flow rates. Okay. So, with the same area you can have you can achieve higher flow rates. Energy inputs are also lower because there is no mechanical or moving part, as in case of like rectangular we saw that there would be arrangements for moving the particles. Circular also you have things rotating in order to push the sludge particles back. So, generally these plate or tube clarifiers, Lamla clarifiers are free of those kind of equipments, and that is why the energy input are also lower. However, it is not very applicable to the larger systems, primarily because there are high chances of clogging, particularly with the wastewaters which may have lot of sediments, okay, a lot of such particles, and therefore, it needs regular maintenance. Otherwise, what happens that the flow distribution does not remain even. Some may get choked, some may get not choked. So, then from other tubes, because your discharge is constant, so you may get higher velocity, you may get those kind of issues coming in the this type of system. So, that is why this restricts its applicability little. These are some of the such systems. So, you can have a plate clarifier like this, where you see that the flow from downward pushed through this, and then the flow will be collected here. This is the kind of tubes, slanted tubes, or this kind. So, this kind of structure and arrangements can be packed for the plate or tube settlers. So, these are the typical design of plate and tube settlers. So, with this we conclude the discussions for this week. We would be having some practical some practice problems, some numerical problems on the discussion that we had. So, that either we will do as a supplementary video, or we will put through as a lecture material some solved tutorial problems and some maybe unsolved tutorial problems for practice purpose, which will be uploaded. So, thank you, and see you all next week.